Hi, good people, welcome back. In this video, we're going to do an example of a two-tailed hypothesis test. Just want to say thank you for those of you who were able to attend our video meeting on Friday afternoon. In the video meeting, we did go over this problem, but I wanted to share it here for those of you who were not able to attend. Please try to attend next week's meeting, again at 1:30 on Fridays. We're going to have a video meeting. You can find the link for that on Google Classroom. All right, please pause the video, take a moment to read this problem for yourself. You can pause it right now. The National Center for Education Statistics monitors many aspects of elementary and secondary education. Its 1996 numbers are often used as a baseline to assess changes. In 1996, 31% of students reported that their mothers had graduated from college. In 2000, responses from 8,368 randomly chosen students found that this figure had grown to 32%. Is this evidence of a change in education level among mothers? So in this question, we are basically trying to figure out if this is a statistically significant change from 31% to 32%. It seems like it's almost too small of a change to measure, but luckily this chapter gives us some very effective tools at measuring changes such as these. And we're supposed to answer these 5 individual questions here. Question 1. Write appropriate hypotheses. The hypotheses that we're going to use here are, is it still 31% of students whose mothers graduated from college, or did it in fact change from that number? That's our hypothesis. So we're going to state that as using the notation null and alternative hypothesis that is presented in this chapter. Our null hypothesis is the boring condition that the proportion of students whose mothers has graduated college did not change and it's still equal to 31%. And our alternative hypothesis, H sub A, is that it is actually changed. So I'm just going to use P does not equal 31%. We don't know if that 32% means that it's increased or perhaps it just deviated from that 31% due to chance. And since we're not investigating whether the percent of students whose mothers have graduated college has increased, they simply just say, is there evidence of a change? That's why I decided to use this alternative hypothesis, P does not equal 31%. If it had said, is there evidence of an increase, I may have actually used P is greater than 31% and used the one-tailed hypothesis test, but it's not asking us if it increased, it's asking us if there's evidence of a change, and a change from 31% just means that it's no longer equal to 31%. And this type of alternative hypothesis is called a two-tailed alternative hypothesis because we're going to investigate the plausibility of obtaining such a percent by seeing how likely it would be for our sample proportion to deviate on either side of 31%. So our next step is to check the assumptions and conditions. Well, the assumptions and conditions for using a one proportion z-test are the same that we used in chapters 17 and 18 when we did confidence intervals and sampling distributions for proportions. The assumptions and conditions that have to be met are the independence assumption, the randomization condition, the sample size condition, we cannot sample more than 10% of the population, and the number of success and number of expected failures have to be both be greater than or equal to 10. That's called the NP-NQ condition. These are the conditions. You can read about these conditions in chapter 17 more if you'd like. They also touch on them a little bit in this chapter, in chapter 19. If you want, you can pause the screen, read the conditions. All right. Is the independence assumption satisfied in this problem? Yes, we can reasonably assume that each individual respondent's response is independent of the previous person's. Is the randomization condition satisfied? It actually says somewhere in this paragraph that these responses were obtained randomly. So they use some type of simple random sampling. So yes, we do have the randomization condition satisfied. the 10% condition. Does our sample of 8,368 people, does that represent more than 10% of the population in question? The population in question are students. I'm assuming students in the United States. So there's no way that 8,000 students comes even close to 10% of the entire population. Sorry. So that is definitely met. We didn't oversample. And the success failure condition is met because if there are 31% of the students whose mothers went to college in our random sample, we would expect to see at least 10 students who said that their mothers graduated from college, right? We'd expect to see that many. And we'd expect to see at least 10 students say that their mothers did not go to college. So we have the success failure condition satisfied. So we satisfied all of the conditions necessary to use a 1 proportion z test. Perform the test and find the p-value. So what we do to perform this test is we actually construct a probability model based on our null hypothesis. Our null hypothesis is that the proportion of students whose mothers graduated from college is 31%. We are going to construct a probability model with that mean, and we're going to use as our standard deviation this familiar formula, the square root of pq over n, where we use p as 31% and we use q as 69%, the complement of that, and n is our sample size here. So we're going to go ahead and build this model, okay? So the mean is centered at 31, and our standard deviation is, we're going to have to calculate that. I'm going to use a calculator here. Square root of PQ P was 31, Q was 69, and to use our sample size of 8,368. 0.0051 if I round it to 4 decimal places. 0.0051. So we're going to build a normal model based off of our null hypothesis. The null hypothesis being that the true proportion of students whose mothers graduated from college is 31%. Let's build that. And I took the liberty of doing that in advance. Here we go. So I counted 3 standard deviations in each direction. And then on this normal model, we're going to plot our p hat. Our p hat is 32%. In our sample of 8,368 randomly sampled students, 32% of them indicated that their mothers had graduated from college. So we're going to plot that right here on our normal model. And we are interested in how likely it is to obtain a result this rare or perhaps further away from the mean in either direction. And the reason we're testing it in either direction is we don't know if we got 32% because there's more people whose mothers graduated from college, or did we just deviate from the mean simply due to random chance? So we should check the other direction too, because it could have just as easily been that we measured and there was 30% of the students had mothers who graduated from college. So we're going to find the area underneath those 2 curves. The area from here and here, add it up. Now, what we can do is make use of the symmetry of the normal model. I'm just going to actually find this area here and then multiply that answer by 2. So our p hat was 32%, and we're going to get that area by using the cumulative density function for the normal curve. And I'm going to set my lower limit at 32% and my upper limit at infinity. Set my mean at 31. I'm going to make my standard deviation 0.0051. And I get this area on the right tail is 0.02495. And I'm going to actually multiply that by 2 to find the area of both parts. And we get 0.0499. So that area under the curve is actually called our p-value. p-value is 0.0499, and what the p-value is, it's the probability of obtaining this result or further from the mean if this is in fact the model that we're working under. If the proportion of students whose mothers graduated from college is in fact still 31%, the chance of obtaining a sample proportion in which 32% of them indicated that their mothers graduated from college is actually less than 5%. And that is typically what we set as the benchmark for statistical significance. So since our p-value is smaller than 5%, there's less than a 5% chance of obtaining such a result if in fact the true proportion is 31%. And that leads us to sort of come to the conclusion that maybe it isn't 31%. So state your conclusion. I'm going to actually state that that's enough evidence to reject the null hypothesis. Since the p-value is 0.0499, there is enough evidence to reject the null hypothesis. Meaning that the true proportion of students whose mothers graduated college is not, or I'm going to say is no longer equal to 31%. All right, so there is the possibility that we made an error where we incorrectly rejected the null hypothesis. That type of error is called a type 1 error, and that's described in greater detail in the next chapter. Is this difference meaningful? The last question here. Since it's only a small difference in our sample proportion of 32%, I wouldn't say that this is a meaningful difference. What does it matter that it's may have increased by 1%? But it is statistically significant. Statistical significance is a slightly different question than meaningfulness. So because our p-value is less than 5%, I would say the results of this test are statistically significant. There's enough evidence to reject the null hypothesis. But in terms of the difference in the percent of mothers who graduated college being meaningful, that's another question. I don't think it's really a meaningful result since it's such a small change. All right, going to upload the actual solution from the publisher along with this video, and you can find that in the Google Classroom post. It might be beneficial to see how they worded their explanation and did the calculations. Thank you for watching. Hope this helps you answer the assignment that was posted earlier in the week. It's due next Friday. That's on the 8th. And please reach out to me on Google Classroom or email me for help. I'm always there to help. Thank you for watching. Bye-bye.